Every day, we top glass screens and press plastic keys, commanding immense computing power without giving a second thought to how it actually works. To most of us, the devices we rely on operate like a sealed black box. If asked to explain exactly what happens in the millisecond between hitting enter and a program opening, most of us would draw a blank. We treat the entire process as if it were sorcery. But there is no digital magic inside that casing. The reality is entirely physical. A modern computer is just millions of microscopic electrical switches stacked on top of one another, clicking open and closed. To comprehend the most complex machine humans have ever built, we need to drop the abstract metaphors of clouds and files. We have to start our investigation at the very bottom, at the lowest physical layer. The blueprint for translating human language into raw physical states dates back to the 1830s with Samuel Morse. Using a telegraph, entire conversations could be sent across continents simply by alternating an electrical circuit between two states, open or closed, which listeners heard as a short dot or a long dash. This diagram illustrates how Morse optimized this transmission. He mapped the most common English letter, E, to a single rapid dot. A rare letter, like Q, required a much longer sequence of dashes and dots. A century later, mathematician Claude Shannon recognized this concept as variable length encoding. His framework, known as information theory, proved that giving shorter codes to frequent data is the basis of all modern data compression. Through these precise rules, the complexities of human language are mapped directly onto efficient binary physical signals, preserving the exact meaning of the original message. Those physical dots and dashes translate perfectly into a mathematical framework, using strictly ones and zeros. This is known as the binary system. A computer navigates large data sets using a binary decision tree, starting at a single point and branching left for a 0 or right for a 1. Each choice eliminates half of the possibilities, quickly isolating a single final value at the bottom. In the 1930s, Alan Turing proved that any mathematical problem could be computed using a machine that reads and writes these sequential binary symbols. What looks like complex machine thought is just a rapid sequence of simple yes or no mathematical choices. To execute that binary math in the real world, you need physical hardware. Early engineers used mechanical relays, later replaced by the tiny solid-state transistors we use today. By wiring these transistors together, engineers create Boolean logic gates. These physical structures manipulate electrical currents to perform basic math operations, outputting a signal only if specific conditions are met, like an and, or not operation. When you link enough of these simple logic gates in a specific sequence, the resulting circuit can take two separate electrical inputs and literally add the numbers together to produce a sum. This diagram illustrates a flip-flop memory circuit. By feeding a logic gate's output back into its own input, it traps an electrical current in a continuous loop. This looping circuit is the literal physical basis of computer RAM. Memory and computation do not exist in the ether. They are tangible, physical architectures built entirely from billions of interconnected electrical switches. Coordinating millions of logic gates in memory banks require a blueprint. In 1945, John von Neumann formalized the architecture that defines almost all modern computers. His model centers on a central processing unit, or CPU. The CPU contains a control unit that acts as a conductor, directing the flow of electrical data between the... This animation tracks the fetch, decode, execute cycle. The CPU fetches an instruction from memory, decodes it into physical signals, and executes the math over and over. This rhythmic loop keeps the machine running. To keep humans from having to manually load those instructions one by one, an operating system is placed directly above the hardware. The OS acts as a manager and translator, automatically allocating the CPU's time and memory resources. The final abstraction layer was built by pioneers like Grace Hopper, who developed the compiler. This tool translates human-readable programming languages into the exact ones and zeros the hardware requires, meaning programmers no longer have to manage individual switches. Software, then, is simply a set of written instructions resting on top of a massive automated pyramid of hardware logic. When you sit at a modern device, striking a single key on your keyboard initiates a physical cascade down the entire stack. Your high-level code flows through the operating system, transforms into binary instructions, and ultimately fires billions of physical, microscopic switches in perfect synchronization. Understanding this physical ladder grounds us. It replaces blind reliance with a concrete mental model, explaining exactly why memory runs out or why processing takes time, because physical electrical currents have to travel physical distances. By stripping away the illusion of digital magic, the computer is finally revealed for what it is: a highly organized, entirely comprehensible, physical masterpiece of human logic.